Welcome to my video on the fundamentals of machine learning. What I'm going to do is walk you through setting up sort of a machine learning pipeline on a data set that's publicly available and just sort of explain what I'm doing in some sort of high level concepts that apply to really any problem or just about any problem in machine learning. First off, what data set am I using? This is abalone data set from UCI. UCI has a repository of data sets online that have been used in research. It's publicly available, makes for great sort of practice. With this data set in particular, what's going on here? Well, what was an abalone to begin with? It's basically a kind of clam, according to Wikipedia. I mean, well, that's interesting. Yeah, so it's a kind of clam. You can see, oh, look at these people. They're collecting abalone. They're kind of large. So the the goal of this problem is to predict basically how old the abalone is, so the number of rings it has. So apparently as it grows it leaves a series of rings. Wait, let me see if there's like a nice picture in here somewhere. I didn't plan on this, but oh yeah, there's kind of, I think this is it. I don't know, don't turn, if you want marine biology, this is the wrong channel, but with this I think this is the phenomenon of, like, there's a couple sort of different surfaces in here, and apparently after the abalone is a year and a half old, it'll start leaving rings for each year it is. So we want to predict how old it is, and I guess researchers are trying to figure this out based upon these other variables. So let's talk about this. So what is, again, this sort of machine learning framework, machine learning problem? What are we doing with this? So what I'm really going to talk about is something called supervised learning. This is, I guess, in my opinion, the sort of core of the space of machine learning. There's a lot of different ways you can set up and solve problems. Machine learning, supervised learning, excuse me, is in this setting where you have some input variables. We're going to call them x. We're going to feed that into some model, usually called like f of x, and then the result is called outcome, and we'll call that a variable y. But what we're trying to do is essentially find this bridge between the input variables and the output. In this case, we have 1, 2, 3, 4, 5, 6, 7, 8 input variables. Just again for sake of terminology, the input can be called an explanatory variables. They can also be called features. And you call them an explanatory variable if you're from a statistics background. If you're from a computer science background / ML background, you usually call them features. The output is, we can call it a response or an outcome. Yeah, so those are the terms. And the model was the model. The model, again, is just this sort of bridge between the two. It finds the association between input variables, output variables. In this case, how does length, one physical dimension of the abalone, how is that related to the number of rings? Basically, it's age. And you expect, well, as this thing grows over time, basically as it gets older, it's going to grow larger. And then there's diameter. This is just another measurement. I think length is probably, if you're looking at it, probably the longest sort of chord you could draw or line you could draw across the abalone. Um, you know, maybe that's the diameter. It doesn't really matter. The machine learning is sort of agnostic to exactly what these are, but these are probably two, you measurements of sort of, uh, you know, one dimension. Height is going to be another dimension. And then we have a few different weight measurements. So whole weight, shucked weight, viscera weight. That's a great word, viscera. It's all the guts. So I guess the part you eat, and the shell weight. So this is really common that we're gonna have. Okay, we have and then we have the sex of it, which can either be male, female, or I guess indeterminate. I guess, which makes sense. I mean, it's just kind of a ball of meat. Like I don't know how to tell the sex of it. That'd all be eyes for me, but whatever. So we're really trying to learn what's the connection between those 8 input variables and the number of rings. So maybe think the males grow faster than females, perhaps. Maybe it's the other way around. I mean, literally, I have no idea. And then you expect, okay, as this thing gets older, it's going to get heavier. So maybe there's a connection there. So right, so there's a lot of you can sort of see the intuition start to form there. But one of the sort of key things is the types of variables we have here, or features we have. So most of these in the middle here are just regular old numbers, right? They're decimal numbers here. If you're from a computer science background, I call them floating point number. Now, sex is a category, right? So there's only 3 different levels for it. So we'll have to do something for that. So that's one thing to keep it in your head is, well, what kinds of data you have, what kind of variables you have, that matters. We'll have to sort of give this a special treatment. So we have to, again, turn these sort of categories into somehow just a number, and I'll show you how to do that in a minute. And then critically is the output. What kind of outcome or response is it? And then it's also it's a discrete number, but we can treat it just like it's a decimal number. So 8 rings, we can say, 8.0 is fine. So what this means is, going back here, not only are we in, I didn't write anything for this, but say, bridge, or connection between input and output. And so that's the model. So again, this is sort of like the stand-in for reality. So whatever process that determines, through time, how many rings the abalone creates and how big it gets. We don't know the sort of real life mechanism there, but the models are basically a mathematical stand-in for that. And we can try a bunch of different models. But appropriately, we have 2 choices here. This is machine learning. We either have classification, so meaning that output or response variable is a category, just like sex, for example, or the other type of machine learning model typically is regression model. So that means the output is just a regular old continuous number. So in our case, we're going to be picking regression based on the data. So just based on peeking at this data, looking at the output is just a regular old number, not a category. We'll use regression. So there's a variety of choices here to use. I'm just going to use, as I've sort of highlighted up here, linear regression. Why? That's always a good question. I have the personal philosophy of, I look at these models as tools, and you want to use the right tool for the job, of course, but you want to use the simplest one that works. And why is that? It's going to be more reliable. It's going to be cheaper and easier to fit to the data. There's going to be fewer surprises or gotchas. this may make a little more sense when you start looking at the data, but you can get the sense that the more flexible or powerful a model is, like the more complex patterns it can find in the data, but also that means it can sort of hallucinate patterns which aren't real. Um, so the simpler models um, are sort of biased away from that. If they're sort of simple, they're kind of it's hard for them to hallucinate patterns that aren't there. So I always go with the simplest thing that works, but this acts in accordance to the principles of all levels. So meaning we can by applying linear regression here and treating it as a black box, we could just swap out a different model that's a regression model and it'll work fine. And a lot of our considerations will be the same, and we use the same process for all of them. All the things I'll show you here is going to be the same. You can just literally change which one you're importing to a different model, and it should all work. Maybe there's some slight caveats there, but that'll be for another time. So I'm going to use linear regression. Also, there'll be kind of an interesting thing that happens along the way here. But now, just in terms of pragmatism, I've created a couple Python files here. This one here I've called regression. I'm going to actually write out the code to train the model, make predictions, show all that kind of stuff. I made another one called explore, so I'm going to explore the data in this, so meaning I'm going to make some plots. I'm going to show what's in there. And then what I have up here is like this sort of preamble to both. I'm using Python. So in the world of Python and in sort of data science or machine learning in Python, NumPy is essential. This is sort of the core library that hooks up to every other library. It's sort of the hub at the center of the wheel of machine learning. And even if you use PyTorch, you give it a NumPy is part of this as well. Usually you're feeding it and transforming it to a tensor, but whatever. It's basically used everywhere is my point. Matplotlib is great. The asterisk on that library for generating figures. I throw an asterisk on there because it's a little frustrating to use from an API standpoint. And then pandas. Pandas is a great library for sort of loading and manipulating data. And you can plot through it. And it turns around and uses Matplotlib behind the scenes. So if you want to sort of duplicate what I'm doing here, you need to install this. And you need to install sklearn or sci-kit learn. That's going to have the actual models in it. I'm, again, just using this as a black box. We're going to look at this as a black box. And then, later video, I'll break down how some of this actually sort of works within the black box. But right now, we're just going to treat it like it exists and just use it and learn something about it that way. So anyways, these are sort of essential, useful libraries. And let's see here. So let's go. Let's start off by reading the data and doing some plots here. So I'm going to use pandas to read the CSV file. Great. So yeah, my pseudocode here. I'm just gonna read the data file and then just generate plots comparing features to each other. Say features to the response, I think, is the most useful thing. So let's see here. So we'll do this. I find it's nice to let's just print off the columns of the data. Oh, so I should note this abalone data set, I've only changed one thing. It comes in two files. This sort of first row is in a different file. So all the names here, I just cut them out of another file, pasted them in here. So this first line is the column names, which is really helpful. Um, Pandas is, it doesn't have to have this, but sort of expecting this. It's just going to make our lives easier, so we can refer to things by the column name rather than, oh, column 0, column 1, etc. Great. So let's go over here, and I like to just print this off just to see everything's working fine. Great. So I can see all the variables here slash column. So that's another thing to keep in mind. Explanatory variable equals feature equals column. They're all the same thing. And this is the sort of classic we call, maybe layman's terms is this is the sort of tabular data setting, which is sort of or fundamental or basic setting. Also usually called the IID setting or independent identically distributed data setting, meaning each of these rows here again is a different abalone, and we're assuming each one is independent, meaning if I know length of this one here on row 5, the fifth one, it doesn't tell me anything really about the one down here in row 12, for example. Each one is unrelated to the others. So, I mean, exploring that more is in terms of what IID means, is a whole another can of worms that I'll defer to some other time. But it's basically this setting where we have these individual records. We're going to look at these individual records on their own. And what would be an example of something that's not IID? One would be time series data, so think the stock market, price of a stock over time. Knowing something about the price of a stock on one day will tell you something maybe about the price of a stock on the next day. So stock market is really volatile, but maybe another time series would be like if you're measuring the height of a tree each day over the course of like 10 years. So then you have a ton of data points there, and if you knew the height of a tree on one day, on 1 month, you'd have a good guess at what it's going to be in the next month, right? It's just going to be either the same or a little bit taller, right? So that's kind of correlation there according to time. What would be another good example is spatial data. So if things are laid out in time and space, I mean not in time, but just space. So if you looking at like, okay, I want to know about how like minerals are distributed in the ground or something like that. If you found some oil in one spot, there's probably more oil close by, right? So that stuff tends to show up in clusters or groups, right, spatially. So that's another non-IID setting. But again, for this abalone, we're just going to say each one of these had this sort of different, path in life or something like that. So knowing, data about one doesn't necessarily affect our knowledge of the other. So that's why it's independent. And identically distributed means it's coming from like the same sort of generating process. So meaning it's the same species. It's grew up in a similar climate. There's, it's coming from the same population of abalone. So it's not like half of these in here are mutant ones that grow the size of a basketball or something like that break that IID assumption. Basketball sized abalone. I mean, there's probably money to be made for that if you can figure out how to do it. I digress. So let's go back to exploring the data. So this is always a good idea. I got the column names here. I'm also going to just print off. So this is how we access something in pandas. We use, this is called a data frame. This represents our spreadsheet over there. We can just ask for the rings column. We can see dot describe if I can type and I don't think. Okay, great. I'm just going to run this bad boy here. And what do I get? I get some useful descriptive statistics. The average number of rings is just shy of 10. The minimum is 1. And the max is 29. Well, that's really interesting. Okay. Um, Great. So we'll keep that info in our head here. Oh man, there's 4,177. I pity the grad student who had to go out and whale these Apple and catch them or something. I'm sure there's some poor grad student story behind this data set, but um, rip for that guy. Well, let's just keep going. Or girl, I guess. Anyhow, or indeterminate. No, okay, never mind. Let's just keep going. So let's plot this data. Particular, what I'm going to care about is this outcome. I mean, I could look at applying them versus each other. What I'm going to find is whole weight versus shucked weight is going to be extremely correlated. Um, Same with viscera weight, shucked weight. I'm not shucked versus viscera. What does that even mean? Anyway, shell weight is going to be connected to the whole weight. But I really want rings versus some of these. So let's look at like length versus rings is going to be a useful thing. So we can do plot, scatter. So scatter plot is going to show that, XY plane and with just points on it. So and the beauty of pandas here, so it's this pandas data frame dot plot, then type of plot, and we can just give the name. So I want to do, what I say, length. We want to compare it versus rings. And yeah, let's just do that. And unfortunately, Panda's API is a little leaky, so I have to call matplotlib.show. Maybe they fix this, but I mean, it's kind of, can't you do like dataframe.show or something? I mean, come on. You have to know it's implemented matplotlib. Whatever. I'll stop insulting it. Let's just go. Okay, so we can see this connection here between length and rings. So like I was saying, as this sucker grows, as it gets older, right, up here, it's going to get longer. So you can see there's this connection here. What's interesting here is there's this sort of, you can see it's like triangle shaped almost. That's going to come back, and we're going to fix this later. So keep that in mind that, yeah, we have a pretty good linear relationship here. So linear regression is going to do reasonably well, just sort of drawing a line through this, so to speak. But the fact that there's some increase, like if you look down here when the length is short and it's relatively young, these points are all pretty close together. But down here when it's out here at 0.7, whatever that is, way more variability down on this end, right? So as length increases, the variability of the outcome changes. This is a kind of sort of, mild nonlinear behavior here. This is in the statistics world called like a mean variance relationship, that as the mean, or yeah, basically of the abalone increases, so does the variance of the rings here, or the outcome. So this is slightly problematic for linear regression, except there's some tricks to this, but that's why I picked this data set. So let's go and look at a different feature here. So another good one here is let's do whole weight. So we'll do whole weight. I'm just gonna rerun this. What do we get? This is great. So again here we can. This is another kind of, and both these sorts of relationships occur. Particularly the other one that sort of straight, but looked very triangular, right? That shows up a lot when you have basically data that's counting something, and the rings are count, right? So it's kind of a slightly different kind of regression problem. So when you're dealing with these counts, that's often the case. You have this sort of canonical sort of shape where it just sort of blows open here, right? This almost looks like, sparkler, like a firework just spraying out sparks here, right? So this is another great relationship where as you increase the x-axis, you see an increase in variability on the y. So like down here, they're all tight. Out here, the spread. So this is the same sort of problem. And we also see, yeah, you can almost draw a line through this. It's not great though. It won't be great, but it'll be okay. What we'll see here is there's kind of a curve to this, right? There's this sort of logarithmic sort of curve to this, and let's file that away in the back of our heads too. This again illustrates a really important point, and I could go through the other features, but you know, was it length, height, diameter? I guess those are just the three XYZ dimensions. Those are all really going to be correlated. The whole thing just kind of, these abalone sort of grow like this sort of meat balloon, if you will. So they kind of grow, I imagine, more or less in all dimensions out, and that's also going to mean the weight's going to look like this, because it's, as time goes on and it gets older, it's getting bigger in 3 dimensions. To gain weight, it's kind of harder and harder. That's also sort of connected to volume too, right? It's going to be more and more difficult for it as it gets bigger, right? Anyways, it's just like this kind of common thing that shows up in nature pretty frequently is you start expanding in multiple dimensions, things start to kind of curve down or curve up, either way, depending on the setting. But this is not surprising that it has this sort of curve here when we're dealing with something so natural as like the growth of sort of the simple animal. Okay, so we can see, yeah, this data, there's something linear-ish happening, maybe with some adjustments. A little foreshadowing there, some adjustments, we'll get this to work. But we just want to see some properties of the data here. So this is really useful. So it's kind of nice to have this script. We're just going to look around and explore. I'm going to continue on. So again, my supervised learning framework, I want to look at these sort of input and output variables, the features and the response, and just check them out, see what's happening here. Notice some interesting patterns we'll come back and deal with. Plus, remember, we have this issue of, well, one of these is categories, and fundamentally, we're going to have to fit everything in our supervised learning framework into just numbers. We don't have really any other choice. So how do we deal with some category, which is really represented as like a string or just a character here? We'll just deal with that in a second. And looking at the data kind of helps us understand which model to pick. So it wasn't like highly nonlinear or something like this, so linear regression will work, but as we could just saw with those plots, there's a little bit of difficulty. So we'll have to deal with that. But that's one reason you might want to look at the data. So by looking at the data, we realize we have a regression problem, and that like linear regression is going to be okay, and maybe with some adjustments it'll actually work pretty good. So let's write out some pseudocode here. So I'm going to load the data. After that, what am I going to do? I need to, and this is going to give us a new concept here. We're going to need to do some, I'm going to call feature engineering, which means we're going to sort of alter or adjust the data in like a principled way. We're not just like making something up, but we're going to sort of take the data and make it more amenable to our model. We're going to sort of make adjustments here, and this happens basically all the time for machine learning. So even if you think, oh, what about these neural networks, do they do it? Yeah, so even fancy stuff like, the transformer based models like ChatGPT, all that, they have some feature engineering going on. In those, what's the engineering? They actually, if they have a sequence of words they're trying to predict, one of the pieces of data, maybe people don't realize this, that they include is they give an index for each word. So they don't just feed in the words, they also feed in the position of each word as well. So they have this thing called a position embedding. But anyways, it turns out it's critical for that neural net to understand the sequence of words is looking at, it's got to have this sort of corresponding integer that goes with it, counting up from 0, 1, 2, 3, 4, right? Just indexing each word. So anyways, we just have to make some adjustments. Like we have to deal with this sex variable that's a category. We got to figure out how to deal with that. That's the kind of feature engineering. And then later I'm going to show you how to deal with that sort of the sort of curviness to the data. That'll be kind of another feature engineering. So we'll do some feature engineering. Then we're going to do a train test split of the data. So this is also called cross validation. Validation. Okay. One of the things here, and this, this example is actually not a good example of this one as we work through it. But one thing that happens as you use more and more powerful models, I mentioned this earlier, they'll tend to hallucinate. They'll try to find patterns in here in this data between, the inputs and the output that don't really exist. Like they exist only basically in the data in the spreadsheet, but they don't exist in reality. So they don't, they exist in the sample. They don't exist in the population, right? So they exist in the 4,177 data points we've seen, but as soon as you grab another 4,000 data points about abalone, you won't find that pattern. So the perennial issue is overfitting. So this is, we're going to help, avoid overfitting. That's not going to be really a problem with linear regression. I'm sure there's some setting you can get to overfit, but it's kind of hard because it's basically our simplest model, or just about our simplest model. So, but it's generally a good idea to take your data, take some portion of it to train the model or to fit the model, as either of those words are interchangeable, and evaluate on the other half that is blind to, and that gives you a way better sense of how accurate the model actually is. So we'll do that. We'll split up the data. This is absolutely essential step. Then we're gonna fit the model to the data. This is also called training the model. Again, machine learning has this funny history where it sort of grew up sort of parallel to some stats. So it's created its own vocabulary. So we use this term training. Statisticians use the term fitting. They mean the same thing. So, and we'll see in sci-kit learn they use the word fit, probably because it's shorter than train. I kind of like using the term fit more, I think. But anyways, it's interchangeable. So just know if you're talking to a statistician, you say train a model, they're like, what are you talking about? Like, I mean, fit the model. They're like, okay, great. So just something to know. And then we're going to, excuse me, we'll evaluate the model. Let's say both on training and testing. And yeah, I've done a lot of machine learning research in my life. I've done a lot of, fitting models in my life. This is basically always the pattern I use. Even if it's, a different setting, doing computer vision stuff or natural language processing, we're always sort of working in this framework, like this sort of data pipeline. If you move to something beyond supervised learning or beyond IID or tabular data to like time series, still going to use this sort of general recipe. Just some of this feature engineering changes and the model changes, but this sort of pipeline is going to be the same. So yeah, I've got who knows how many scripts and projects, etc. on my file or on my computer or in some Git repository somewhere that basically have this sort of blueprint. So let's just go ahead with this. I'll be running this multiple times here, and then kind of adding to it. So whoops, I'll read the CSV. Abalone here. I don't really need to do that. Okay. Actually, for my convenience, just kidding, I will. So I'm going to print off the column names. Columns. Um, run this. Okay, does it work? Yes. So next thing, so first things first. Our first kind of feature engineering is how do we deal with the sex variable? The trick is we're going to introduce basically new columns, and we'll have one for male, one for female, and one for sort of I, indeterminate, whatever that means. Um, and the values can take on in the column, say for sex male column, if this is an M in the data, it's going to be a 1. For anything else, it's going to be a 0. So sometimes it's called an indicator variable or categorical variable. Usually how this is represented is just zeros and ones, so sort of binary category. That way, it sort of mathematically makes sense. It's male, not male. When you sort of crack open the model and look inside, multiplying things, you know, by 0 or 1 internally actually make a lot of sense. So this is a really common trick. So common, it's just it's just built into pandas. So this is gonna be a lovely part from pandas. Get dummies. Get dummies. What we're gonna do is we give it our data frame again. So there's that spreadsheet. We're going to give it some list of columns to change. So I'm just going to give the sex column, and then there's a D type, and we're going to give it float. So again, in this machine learning world, all we have to work with are at the end of the day are just either integers or floating point numbers. A lot of times we're just going to use everything as a float. So yeah, so we change this. Oh, let's go ahead and you can just print this off. Give me this nice little summary here we can see. So I'm just going to run this. Yeah, so thankfully it doesn't just print all 4,000 rows. We can see, oh, we have 11 columns now. Before I had 9. So there's, like I said, counted up before, but there's 8 explanatory variables and 1 outcome. What happened here is it added on these new ones. This get dummies function, that's what it did. So it took the data frame, removed the sex column, then added in 3 new ones. So that first row here is male. So if we look at what it did is it put in a 1 for it, and for the female and indeterminate columns it put in a 0. Let's look down here. Was it like the third row? Oh, okay. There we go. Sorry, I was on the 4th one. It's like, shoot, just screwed up my whole example. I saw the 4 there and I couldn't forget it. So yeah, we have sex female here. Okay, we have F there for female. We get a 1 there and 0s for the rest. Right? So this is one form of feature engineering. This is, if you roll back the clock, 10 years, there's a lot of this kind of stuff going on. This sort of shoehorn problems into this machine learning framework, and often what this meant is just somehow coming up with a lot of these indicator variables, including natural language processing. This would be, this was the original way of representing words. So instead of male and female here, it's like, well, does it have the word, book? There's a 1. All the other vocab columns are 0s. Anyways, I'm going to too many tangents, but this is one still very common form of feature engineering. It's just how we're going to have to deal with this categorical data. There are sort of, you can think kind of alternatives to this now called embeddings, but that's a whole nother topic for a whole nother video, but this actually worked just fine for this. Is we introduce these, again, 3 new explanatory variables, aka features, aka columns, for the 3 different actual values we see here. So for female, indeterminate, male, right? So hopefully that makes sense to you. So yeah, we expanded our data set in some sense by bumping out these columns. Pandas makes that extremely convenient for us. So that's a big win for pandas there. I was a little skeptical at first about pandas, but it's really come through with some of this stuff. Writing this code by hand is just annoying. It's wonderful that it exists. Um, so Presto, we did some kind of feature engineering. We'll come back and do a little bit more of this later. So let's move on to train test split of the data. So now that we've sort of get rid of this one line here. Now that we've handled this problem of that sort of categorical variable, we have just a nice data here with just regular old numbers in it. We have to do that split. So we cross validation. It's anytime we're going to take our data set up and cut it into pieces, and withhold some, fraction of the data to be blind for our model when our models fit. So to the model, it doesn't even exist. And then we can, after we fit the model, we go back and and test on that held out data set. Like I said, it gives us a much better sense of how well does this model actually represent the data, how accurate it actually is. It gives us a sense of what we call generalizability, or generalization. How well does this model actually generalize the new data sets, which is really the purpose here is we want to train this model. Now, if we see new abalone, but we don't crack them open and look at the rings, we just measure their weight and their gender, etc., or sex or whatever, and we feed it into the model and just tells us the rings, and hopefully that'd be accurate. So that's what we're really aiming for, is on future data sets, does this model work? So that's what cross-validation sort of simulating is. We're just taking a data set, just pretending we don't have part of it, then pretending we just get a new that held out part for evaluation to see, like, well, this is actually generalized. Okay, so let's use train test split validation. A few things here. One thing about machine learning in general, a lot of sort of processes in here will have some random aspects to them. So what we want to do is go to NumPy, and since a lot of things I'm going to cover use NumPy, we want to set the seed of the random number. So that this is for reproducible results. Reproduce that. Is E in that? Is that what it is? Forget it. Maybe my vocab is too big for it. Okay. And where this is going to come up is the train test split. So as soon as we come down here and ask it to split, it's going to shuffle the data. So it's going to just, shuffle the deck, so to speak, which is one way, it's going to be helpful that, the data looks somewhat, to the naked eye, random in here. It's not like, as opposed to having all the males, then all the females, then all the indeterminate. That'd be a problem. So by shuffling it, we can avoid that for us. Maybe we don't need it, but so what we're going to use is, so we have to do from sklearn model selection. There's another turn from this, and then we do train test split. Let's see here. Am I in the right place? Let me look at my notes. Yeah, I'm in the right place. Oh, I have to say this. Yeah, train test split. Okay, forget it. Okay. So what this is going to do is it's going to cut up our data in terms of rows. So we're going to have all the same columns, but it's going to give us some fraction of this data. So what I'm going to do is say, give me 70% to train on, and then let's use 30% to evaluate. So let's do that here. And how this particular function works is it's going to return 4 values. The first 2 are the inputs, but its inputs cut into 70-30 split. So this is going to be 70%, 30% of the inputs, and then their corresponding outputs are going to be here. So we'll y train and then y test. And we'll do train test split, and we give it oh, sorry, I got ahead of myself slightly. I need to before I do this, I need to set up, let's pull out what we need to do is just pull out these explanatory variables. Let's call in the features, just put them in their own data frame, and then grab the output, the rings, and put it in its own as well. So let's do that here. And what we're going to do is, see, I told you I was skeptical about pandas, and it's because of this business. There's this location index, and then we get this colon stands for all the rows. And then I can say where the columns is not rings. So this is saying, okay, go to my data frame. Give me, access things by location. Give me all the rows, which is colon means, but basically drop the rings column out of here. So this is just the inputs. So let's say get just the inputs, which we're calling features. Then let's get the response, which is going to be this. So we can just pull out, it's kind of easier in pandas to just get what you want. So I can say, just give me the rings. This is saying, give me everything but. I mean, that's sort of awkward. I mean, just look at that that little chunk of code there. I mean, it's not the most satisfying thing in the world, I gotta say. I mean, could you have, like, some method on it, like df dot, I don't know, all columns but, or something, and you give it some column names? Anyways, let's move on. So I give it a list of columns I want here. So this is going to give me back the just that one column. Now, I'm going to convert it to NumPy arrays. Why am I doing this? Again, I've had been burned slightly using just pandas directly. It probably won't matter at all for this example. You could just skip this, but I think of the NumPy array as sort of the sort of data format we can give to any of these sort of machine learning statistics libraries that are out there in Python. It's just this sort of universal data structure here, and Pandas is a bit newer. It's built on top of NumPy, which is, I mean, it's got a lot of nice features. Don't get me wrong, especially like the plotting stuff. But at this point, I'm just going to leave sort of that Pandas stuff behind. I just personally use it for doing this kind of thing, like creating those indicator variables, or when we see we can do some other transforms of the data. That's nice, but we'll just kind of leave it there. Now, for what this was, now I can get back to this. What does train test split do? We just give it the input, we give the output here, features and response, and let's see, it's going to be, train size, that's right, is, I'm going to say 70% here. And maybe this is a magic number. I could define something up above, but we'll leave it be. So anyways, what this is going to do again is it's going to take those 4,177 rows, and it's going to give me 70% of that. So, probably like 3,000-ish rows out of features, put them in the train. It's going to look up the same corresponding output, so it's not going to scramble input-output combination, don't worry, and it's going to put that in Y train. The remaining 30% of features is going to show up here in X test, and the remaining 30% of the response is going to show up here in Y test. So that cut our data set up, right? So again, this thing is there's 30% of the data just left out. Is our models can be blind to it while it's fit or trained. This means that we can go and evaluate on the test set later and get a better sense of how well this generalizes. Now, slightly spoiler, linear regression does not really have this overfitting problem in general. We're not going to see a wild difference there. It'll be a little difference, but not huge. Now, if we substitute this out for a feed-forward neural network, it's very easy to get 100% on training and then something much lower on testing. So that's example overfitting. It's really easy to do that. So you can hallucinate very easily with these more powerful models. But anyways, almost there. We got they actually make the model. So I'm going to make the model linear regression here. There's no other. Well, there are some what we call hyperparameters we could change. That'll be a whole other topic on what we call model selection and tuning. That there's a lot of other sort of basically settings for each model we can sort of adjust, and but that's this whole thing, a whole another sort of topic. We don't really there are some, it's not much for linear regression. That's fine. Leave it just sort of very vanilla like that. And now the beauty of sklearn. So this is again where this come from. I'll just jump up to the top here. This came from sklearn linear model. So just using this, I really like sklearn. I think it's a very well designed, really high performant library. It's really, they did a great job with this. It was not always the case. Roll back the clock like 10 years is, the hellscape of no machine learning tools. Now sklearn's beautiful. Anyways, for the fit the model, again, this is like essential machine learning. You got to have supervised learning, rather, that we have to have the input here and output. And the model's going to fit. It's going to find that connection from the input to the output, like acting like that sort of bridge or this sort of mathematical substitute for the real process. That's what the model would be. Sort of find patterns in this input that connects it to the output. And the pattern of that linear regression, you can get, by its name, guess what it can find. There's a linear relationship. So, think back to, high school, that y equals mx plus b. It's just going to be some, for each feature in here, it's going to learn some, we call weight, so which is really some sort of let's say quantification of this variable's importance, and it's going to multiply it. So it's going to be basically that slope in terms of y equals mx plus b. M is sort of the weight, it's the slope. That's what linear regression is going to find. Basically, the slope is going to be the connection between, say this feature and this output. And it's just going to learn a different weight for each one. So it's going to say what's the importance of the length, the diameter, the height, whole height, blah blah blah, each one, and then each of the three sex variables. Each one gets a weight as well. So we'll fit that. It's linear regression. I mean, it's computationally extremely cheap. I mean, you can run on a graphing calculator, for heaven's sake. So it's another good reason to use it if you can get away with it. So yeah, that's it. So we just treat it as a black box, or say, hey, find the connection between input and output here. Let's check out how it did. So after we did that, we got to evaluate the model. So how are we going to do that? We're going to make predictions, and this is really how supervised learning works. Is it tries to make a prediction for some input. It says, well, okay, given this new abalone, how old is it? How many rings does it have? And then we just test that versus the truth, right? And we're just going to fundamentally just come up with apply some way of discerning, measuring really, how far is it from the truth. And that's what it uses during when it fits, or trains the model, let's say, it's going to do some process of making predictions, comparing that to the truth, and then based on how bad the prediction is, like how much error there is, make adjustments to the model. So if it makes bigger mistakes, it can make bigger adjustments to those weights. Smaller mistakes means smaller changes to those weights or to the model. So, well, first of all, since I'm talking about the weights here, let's just check it out. So in sklearn, there's this stands for coefficients, and there's also an intercept. So the coefficient is the weight per feature, so it's just some number that multiplies each feature. The intercept is, again, if you're thinking y equals mx plus b, this is the plus b. So this changes where the the line that linear regression is hitting the y-axis. It's kind of connected to, generally speaking, the average size of an abalone, right? So that's going to not exactly peg where it's on the y-axis, but it kind of uses that to sort of get in the neighborhood, and then all the other coefficients on each other feature sort of dial the line into where it needs to be. So we're just going to look at this. Now it's kind of hard now that we have multiple if we had just two variables like shell weight versus rings, we could plot that. This can be a little hard to plot. I'll do that in the end, I guess, or we'll do something similar for like error diagnostics. But what this is going to show, this first one is just going to be the weight, or sort of the importance of each feature. So let's just go ahead and run this. So what does this mean? So if you're a statistician, you really, really care about this. If you're a computer scientist who's in machine learning, you're like, okay, whatever. So the statistician they don't really care as much about how accurate was this model. They want to know what is the connection between input and output. That's the whole point of stats, is like, this is saying, okay, was this the second column in on our, here, let me change this so you can see the real columns after I modify the data. Rerun this. So what does this mean? So the second one's diameter. So diameter is relatively important. I mean, yeah, there is a question of scale here, so there's a lot more nuance to it, but basically for every one the diameter goes up, the number of rings goes up by 11. So I guess diameter is probably going to be a very, on average, small value. So, but as it changes at all, it contributes a lot to the number of rings that's there. Let's go down the list. So, let's just look at length. Generally, slight negative relationship. That's kind of interesting. Or height is, so this means, I guess, as it gets longer, you expect fewer rings. It's a little bit surprising. This is, I mean, we'd have to go and look at the variation of this and look at the standard error and the standard deviation and basically perform like a t-test on the weight to know if this is real. My hunch is this maybe not like a real connection here. Maybe length is irrelevant, so that's a possibility, let's say. We're not really going to care too much. We just care about the accuracy in the end in the machine learning world, but we haven't quite got there. But so there's a connection, let's say, between height and number of rings. So that's what this is saying, is height goes up, number of rings goes up quickly. The weight, whole weight, there's a big connection there. Shucked weight, unfortunately I don't have a good shucked weight. I guess this is, my guess is like this is shell weight. Shucking, I don't know, they might have cut some stuff off of it, I guess. I don't really know. Visceral weight, I can guess this means the actual meat inside of it, and that should be let's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Is that true? I guess so. So I guess as visceral weight goes up, it has a negative connection with age. Huh. So there must be a bunch of young, fast-growing abalone and older ones that tend to stay small. That's a little bit interesting. Oh, the shell weight is really connected. So I guess maybe as the shell gets, that kind of makes sense actually. That the older the abalone is, like the thicker its shell gets. And then, oh no, I've got rings in here. Forget everything I said. This is terrible. Oh my goodness. What have I done? Forget all that. I mean, maybe the first few are fine, but I got rings in here. So that's, I don't know. That's probably not. So this, it was not actually in the data when I fit the model, but it was in my explanation of what's what. But shoot. So let's just take this. No, let's not. Let's just copy that. Let's print off. Shoot, let me go back. Oh, okay. No, I want just this columns. Okay, go to this. Okay, that would actually give me a better connection. So this should be the let's see here. Yeah, so this is gonna be the same as this features thing. The actual columns there. Okay, so I wasn't totally lying before. Shucked weight, visceral weight. Okay, that's fine. Shell. Okay, so I wasn't just totally making stuff up. I guess it would. Okay, great. Yeah. It all sort of lined up. It just was off at that one point. Okay. And yeah, these are sort of the intercepts for, well, or let's say this is the contribution of it being female, right? So if it's female, that adds a little bit more to the age and so sex. So these are not gonna. It makes sense. These are about the same, and this is a little bit negative. That's kind of interesting. Maybe if there's indeterminate sex, then there's something kind of off with its development. So maybe it's not gonna be as grows old or something like that. But where you'd really expect to see, I think, this interaction is maybe like between it being female and maybe the weight, or the male and the weight, that there be interaction between these two features. That's not part of linear regression at all. So that's where I'd really expect this to impact this, and that'd be a good reason to try out other models, because that's what, like, decision tree is going to get you, or that's what like a neural network is going to get you, is like how are these two things connected together to produce a change in the number of rings. Like how do those two things together predict the number of rings? So sometimes there's variables in our data that are kind of like a catalyst, right? That they don't have a really direct connection to the output, but they do have a connection to another variable in here, and together, when you put them together, they're really predictive. I mean, I don't know if this is a great metaphor, it's just come off the top of my head, but you can think, well, it's like a match and gasoline, right? On their own, there's not a lot of fire. You put them together, you get a lot of fire, right? So yeah, if the match on its own, it's like, oh, there's a little bit of flame, and then if you look at the gasoline just sitting there and in a can, okay, that's not burning at all. But you drop the match into gasoline, hello, we've got a lot of fire, right? So that's kind of that sort of catalyst or interaction effect. Anyways, that's a whole nother topic for another video, but this is just, I'm just going over some concepts of like maybe why would this be sort of deficient. Is, well, neither of these probably matter a ton on its own in terms of predicting number of rings. So I guess this is maybe saying that males live slightly longer, I guess. That's kind of interesting. but I really expect this to interact with these other variables like weight, length, diameter, maybe the basically the physiology or the shape of these abalone is different if it's male or female or something like that. And that together might tell you more about how old it is. So maybe, like for example, maybe this length doesn't matter. It's not connected if it's a female to its age at all or something like that. If it's a female, okay, it just doesn't get longer past a point or something like this. But if it's male, it keeps doing it. I don't know. I'm just making that up, but that'd be another example of interaction. And then this is the intercept for the model. This is the b, y equals mx plus b. That's the intercept. So that shows you where the line's sort of starting on the y-axis, so to speak. Or really, this is technically training not a line, but a plane if you want to think about it mathematically. But anyways, I'll try not to ramble too much more here. Let's just actually get to error measurement. So first thing we need to do, but anyways, let me, I'm going to ramble a little bit more. But anyways, this is the product of training, of fitting. So this is, like I was saying, there's an importance per variable here, a weight as we call them, and this is sort of the bridge, right? So we have sort of the mathematical form of the line y equals mx plus b, the process of, except we have multiple x's, right? So we have y equals m1 plus x1, m2 plus x2, so on and so forth, plus b, right? So this is the outcome of fitting the model. It's just figuring out what all those sort of slopes or weights are. This is identical to when we're training a neural network, for example, which is on the other end of complexity. In the end, all it's doing is just figuring out a lot of these weights. Another word for this is parameter. It's a parameter for the model. So we're just trying to find, basically fit the parameters to the actual data. This, people have probably started to hear, this term parameter more because of the large language models, right? They say, oh, ChatGPT has billions of parameters. Well, it has billions of these kinds of numbers which connect some part of the input to the output. Now, those models, the trick is, for the neural network stuff is, it's just like a model chain to a model chain to a model chain to a model, where the output of one, you can think of it as just a series of them. So you give the input to one model, produces the output. Now that's the input for the next model, and so that's how you can get, generally speaking, a billion parameters. You used to do that a lot. But anyways, enough. Okay, now enough ranting. So anyways, we have this fit model. It really just means it finds these parameters / weights. You can use those words interchangeably. Now let's go ahead and just see, well, how good of a job did it do. So let's look at, I'm going to do, let's see the predicted y, so the predicted number of rings. Let's do that. So use the model, and there's just a lovely method called predict. We're going to feed in the test data. And then let's go back and just actually, maybe I'll do this. Okay, Vim key's getting out of control. Let me do this on the training data as well. I'm going to do x train. So we'll just go ahead and see how good of a job it did on the training data, and we'll go ahead and see how good it did on the testing data. And there'll be a little bit of difference, sure. So what we're going to do here is I'm going to just print off a lovely message, say training error. So lower is better. So when we're talking about error, we want that to be 0. So that's our mistakes. We can always kind of reframe it or flip it around, turn accuracy by doing, typically something like 1 minus the error. And then higher is better. We want to get up to, 100. An intuitive measurement of error for this case, we're going to use mean absolute, if I can spell, mean absolute percent error. So what this is going to do is take the truth, subtract off the prediction, right? And then we're just going to take the absolute value of this and then just, average it. So this is, my pseudo-mathematical thing here. I'm writing in a comment, but we're just going to make a prediction like we just did for each model, for each abalone with the model. We're going to then turn around, since we know the answer for it, we're going to compare the answer, the truth, with the prediction here. And how do we compare it? We just subtract. So that gives us how far we're off of the truth. And then we just use the absolute value because we don't care if we're under or over. Like, we don't want those, we don't want our under and over to sort of cancel ourselves out. So we'll do that difference. We'll take the absolute value, so that will just give us how much we're off in general, and then we'll just average it out. So this is in general how far we're off. Oh, and to make it a percent, sorry, the percent, I gotta divide by the truth. So, because we're talking about number of rings here. So if this, if we divide by whatever the true amount is, that's going to give us, that's going to sort of normalize this down to a percent. So we'll get something, between 0 and 1, and then it's averaged out, still say between 0 and 1, but it gives us a percent of how many percent the model's off. So I already imported this from sklearn metrics, mean absolute percent error. I mean, that's a mouthful. That's so lovely. It just says give the true one there. Is that, double check my notes? Yes. So yeah, we'll do what do I call it? Oh yeah, y train. So this is the true number of rings, and then we'll do pred y train. We'll do this down here and do testing error, and we'll just change this to test. So y test. So this is our cross validation step. We're gonna, another term for this is out of sample accuracy or out of sample error. That's what the statisticians say. So meaning the sample is what we fit the model to, and then out of sample meaning data we haven't seen before. Anyways, enough talking. Let's just run this. So yeah, this is a pretty common story. So this means we had 15% error, just shy of 16%, and it's just slightly higher in testing. So that's what you generally expect when you go from training to testing. You're gonna basically guaranteed, maybe not strictly speaking, but 99% of the time it's going to go up when you go to testing. I'm trying to think if I can remember any case if I went from training to testing and saw lower error. I mean, that's just extraordinarily rare. But anyways, so you're typically going to see the error go up. It only went up a little bit. But this is sort of one of the benefits of linear regression, is this is usually the case that the error's going to go up, but it goes up by not too much. So great. So we trained the model, we loaded it, we talked a lot about all these different concepts. I'm just going to throw a couple more things at you before I let you go. But so we have the 16% error. Let me comment one other thing. This mean absolute percent error, this is really intuitive, right? So I can say, on average, this model's 16% off. Okay, I can go tell that to, my mom or something. She'll know what I'm talking about. The more common metric is something called root mean squared error. And what that's going to do is it's going to take... I'll explain why this is more common, but it's a truth minus a prediction again, but squared instead of absolute value. Why? Because it has that same effect of if you're over or under by the same amount. So if the difference between truth and the prediction, let's say, is just like 0.5. It doesn't matter if it's 0.5 or negative 0.5. When you square it, it ends up being 2.5 either way. So basically, over or under is the same amount of error. But squaring, why this? Basically, it makes the math easier. So if you're analyzing the linear regression model fit with this called loss function, this kind of error, like the math works out. We know how to deal with something squared is actually very easy to deal with when you're talking about basically calculus. Absolute value, a little trickier. um, it's a little bit trickier to deal with. So they just picked this because it makes the math on paper a lot easier. It doesn't make a lot of sense, but anyways, I didn't quite finish this. You do have to, so go through this, do truth minus prediction, square it. You got to average it, or let's say sum it up actually, and then do the square root, and then divide by number of data points. So maybe I'm wrong. Maybe that's averaging on the inside. Regardless, it's not a big deal. If this 1 over n goes on the inside or not. Kind of slipping my mind at the moment, but yeah, this won't. This is not as intuitive, but this is generally speaking what you see if you start digging into the math behind a lot of these regression models, like linear regression, or even when you're starting to fit neural networks, you're going to use this mean squared error, or root mean squared error. No, I'm just going to take this back. This goes on the inside. I mean, the name suggests it, right? So this is really just average. I'm gonna stake my claim there, because it's root mean squared, right? It's kind of the same order, right? See that? Root mean squared. Okay. But anyways, yeah, I'll kick out a number. It'll, 7% will be, okay, you're 2 rings off or something, right? But it's not really rings because it's like squared averaged rings with the root of it. So it doesn't end up being exactly what you think. This is going to be way more interpretable of like, I'm 16% off. I can do 16, like if it's 10% off, I don't know, 10 rings. It's like, okay, I'm usually 1 ring off, 1 year off. Okay, and then 16%. So yeah, you're up to 1.5 years off. Okay, that makes sense. In general, you can feed those explanatory variables into, length, diameter, height, etc. You feed into the model in this case, and you end up making predictions. In general, like a year, 1.5 rings off or something like that. So that means you could also use just mean, set percentage. You can just do mean absolute error. Maybe let me just do that too. So, mean absolute error. So that's like, again, how many rings am I off, versus the percentage of when I'm off. So let me just go import that. That'll be a nice little addition here. But anyways, even something as simple as this, let's go on and on and on. Mean absolute error. Okay, let's just run that. We'll see. What am I saying? Yeah, didn't I just say like a ring and a half? That's okay. Great. Mental math win. Yeah, killer. So that's what that means. Is in general, on average, we're a ring and a half off. So now, I mean, this has gone on a lot longer than I thought, but I want to throw one other thing at you. So there's one other step. think, well, can we do better? Can we do better than this 15% error? Um, yes, we can. And how do we get some intuition that there's maybe something we can improve? So if I do scatter plot here, and I'm using, matplotlib directly, so I'm taking, my life in my own hands by doing this, but, you know, for this sweet, non-YouTube money, we're just going to do that. So, oh, right, put a colon in there. So I'm going to do, again, this means, okay, I've got my, sorry, dyslexia moment. I'm going to change it around. Okay, so my X features, those input variables, give me all the rows. Just give me column 1. Why did I pick that as diameter? Okay, let's just see that versus, we're going to do the predicted Y minus the truth. Maybe I could turn around the other way, but whatever. And this S2 is just the size of the point I'm going to plot, so it's just aesthetics. Don't worry about that. What I'm going to show to you in a moment is a connection between the diameter and this is really the error, right? Kind of roughly speaking. I guess I could do like, well, let's just do that. I know this will work, but I'll fiddle with it in a second. Basically, this is, the core of the error, right? I turned it around, but it doesn't matter. It just flips the sign, right? This is I'm calling it diagnostic plot. I can't believe I spelled that right. Fantastic. Anyways, this is a diagnostic plot. So these are also called residuals. You'll hear that term, residual. That's kind of what's, residual means what's left over. That's going to be the error, right? So the difference between what we've predicted and what the truth is, that's what we couldn't basically model. Let's just run this and see what happens. Oh boy. So we get this. This is somewhat reasonable. So you can see 0 here. You can draw kind of a line between this. This looks pretty flat. Like if I was going to put a line between here, this looks somewhat flat. Or you could say for a lot of these points here, there's just a big mass here, but there's actually something kind of pulling us down, right? Something pulling us down. There's all this stuff here. So this is basically the evidence of sort of a systematic bias of our model. Like it cannot handle these points down here. There's just a big error, -10, so this big mistake down here. For certain larger, and you can see it's not when the diameter is small, it's when it's large. Remember that when I go back to this exploratory, let's just do diameter here. Diameter. Let's just run this. Yeah, remember this sort of shotgun blast here? This sort of, or it's maybe, let me spin it positive. It's like a little emoji of like the, right, the little confetti cone thing. Happy New Year's, right? So we got this sort of triangle shape. This is a kind of nonlinearity, right? As we increase the size, the variability blows up. Okay. We can fix this. We can fix this. No problem. Now this is, and I promise this, we're going to do a little more feature engineering. Let's go and let me just take all of these. And this is kind of like somewhat old school, like stats move. So this is something probably like a more sophisticated model just sort of figure out on its own. That, there's, where'd it go? There's not a strictly linear relationship. There's this sort of expanding cone. Maybe more of the other one where I had, what did I have before? I had whole weight. Yeah, this one's a real good one where you get this sort of curve to it. This is something more of like a neural net's going to figure out better, so kind of the curviness there on its own. The spread is really annoying. So we can use this sort of trick. This is kind of feature engineering. Let me go through here and just write up some little code. So I'm going to say for column in, and I'm going to paste in all these boys. Do some real annoying stuff here. I don't know if there's got to be a better way to do this, but you know, time recording's late. I'm just gonna, you know, muscle through this here. Okay, a lot of clickety clackety. Let's wait for it. I gotta make these all strings. Now I'm gonna include rings in here, so this is, well, it's not feature engineering. Yeah, this is another sort of old school stats trick. Is like, let's take all the data, and so we're going to take the column, we're going to update it, we're going to change each of these columns. We're going to say, hey, column, why don't you apply natural log to it? So we're going to take the natural log of everything. Now, this is sort of, was it like an, some people consider this like a no-no in stats. I'm not like cheating in any way, but if I'm really concerned about the true connection between the diameter and the number of rings, and I want to make some inference about, oh, as the diameter increases, how many more rings does this add? Yeah, taking the log of everything is gonna sort of mess up my interpretability. But for prediction, it's fine. So I'm just gonna turn everything into a log. So let's redo this exploratory plot. So wait, let's look at, Happy New Year. Let's take a look at this. Let's run this. What does it have? Whoa, look at that. Now this is this is great. I mean, there's some variance here, the sort of width of the points going across, but this is way more linear, right? We can just draw a line right through the middle of that. So whole weight, number of rings, we solved that bad boy right there. Now, let's go up here and let's, so we're sort of transforming the data. And actually this is, I kind of slightly take back my comment from before that actually this arguably is what, like, not just a neural network is going to do, but a deep neural network. So this is caveat, I'm not taking it back, but caveat, this is what a deep neural network might do, is it's transforming the data in a way to make it work with linear regression. So, I've made this sort of deep regression model for some other project. It's computer vision project. It ends up with linear regression in the end. So it's actually the final step, but there's this all these sort of complicated computer vision, convoluted neural networks, literally called convoluted neural networks, to start understanding the images, but it's just setting up linear regression with the easier problem. That's what I'm doing manually here. I'm just saying, you know what? That other problem is tough. Here's an easier one, just by applying this little mathematical trick. Now let me rerun this with diameter. That was also another little cone. Boom. This is now, there's no cone here. So this is kind of even width the whole time. Maybe slightly, no, it's just noise. So it's just kind of even width the whole time. It's really lovely, very linear. So this, I'm going to take my little transformation code here. I'm going to go back over here, add into my feature engineering. Boom. We're going to take a look at this. And let's just take a nice little run with this. This is going to be good. So this is going to go through and transform all our data. And let's give it a little run. And what have I done? Oh, yeah, I forgot my other little point in here is that some of the rings are 0. Some of them are 0. So we take the natural log of them. It's going to go negative infinity. So I'm going to do a slight adjustment. You can either add in just a very small number, like 0.00001 or something. I'm just going to change it effectively from rings. I'm going to change to years. So, I'm going to say rings equals rings plus 1.5. This should be fine. Too deep in the video to go back anyways, so this work. No. Why does this not work? let's see here. There's another variable here that's, now I'm off script. Unfortunately, there's another variable in here. Need to go through and figure this out. One of these actually has a 0 in here somewhere. Is this probably this? No, it's not that one. It's not rings either. This. Okay. Anyways, this is bumming me out. Hold on a second. Let's just hack this slightly. Well, let's just go back over to explore. This is a better way to do it. So let's do let's look at length pre-transformation here. The mean, the min. Okay, so it's not length. That's not hurting us. One of these is basically 0, I think, is my problem. Let me just rerun this slightly. Min and height. Height has its minimum value 0. I found it. This has to be it. So, forget this. This did not fix our problem. We're gonna get rid of that. Height is gonna be height plus a little bit, just a teeny bit. Cross our fingers. Boom. Saved it. Whole buddy. Now look at this. Now, shoot, I should have given you a better before and after. This is a diagnostic plot. Remember there's this huge splotch down here of a bunch of points? Those went away. Those got sucked up here. This looks a lot flatter. That means I removed some sort of systematic error from the model by making everything log. Let's go through and look at... Oh, look. Well, look at this. Oh, this is another little issue here I can fix. This is like an underflow issue. It's a fitting issues, probably, or overflow or underflow of a numeric issue. This is probably because when I introduced these indicator variables and I have that plus b for the line, I think that was too much. Let's try this. Let's try fit intercept false. So we're going to, instead of y equals mx plus b, is this y equals mx. We're ditching the intercept. Let's rerun this. Still this huge. Oh, let's go back. I think one of the rings. I need to do this too. Okay, let's just do this. Boop, boop. Okay, there we go. There we go. One of the number of rings. It might have not been. Let's go back and explore this explorer thing. Let's go look at this. Stop and rerun. Minimum 1 for rings. Wait, let's think. Yeah, so what's happening here is if you take the natural log of 1, that's 0. That means there's a divide by 0 basically ish error happening somewhere in here, which was giving me that sort of insane error amount. So if I just added that 1.5, so we're operating in years instead of rings, problem of, crisis averted, right? So now we get sensible error output. So that's what I did there. So sorry, there's a bunch of me jumping ahead, but look at this. The error before, remember, it was about 16. Now it's down, wow, way lower to 5%. Now that's in a log error, that's in log units. So maybe that's cheating slightly, but I definitely the model is going to be a better fit. Like, this just has to be a better fit for that. We can, and then if we wanted to, we can raise this to, e2 each result. So maybe I can do that. Maybe if I do, let's just try that out. Let's just see. So this is sort of undoing the log. I can do that, and I can do that for my train. I'm going to say is, let's just exp each one. Oh, that would have been fun. Swap train test right there at the end. Let's see. So now we're just sort of undoing that log I did before up here. After effects, so we should be back in rings instead of log rings. Let's see what it is. Hey, so it did. We went from about 16 down to 12% error. Hey, and then mean absolute error is still 1.5. It was a decrease. You know, it's a few percentage points here. Okay, it's not like a massive change there. But we did improve the model. So this is just another win for feature engineering. I just want to show you that, yeah, if you want to sometimes adapt, it sounds strange, but sometimes you want to adapt your problem or the data in some sense to meet the model. And arguably that's what super complex models are doing anyways. So I'm just going to give linear regression a little bit of help here by getting rid of that big, cone, if you will, that sort of, big triangle shape, that annoying Happy New Year's cone is gone. Nice sort of cloud point along the line here, right? So I basically sort of fixed, air quotes, the data by transforming it. And basically, I'm doing linear regression in log space instead of normal linear space, and it ends up being a more accurate model. So this is just another kind of feature engineering. So this is just one of these sort of tricks that kind of come up. So like the log thing is this classic old school stats thing. There's a bunch of other tricks like creating these indicator variables and other things, but the point is the model needs to sort of be a good match for the data, or it's not going to work very well. And then sometimes we can sort of do some extra little engineering tricks as a pre-processing step to sort of make our model be more successful. And that's another sort of key thing that does not get a lot of airtime. You hear people talking about machine learning, talk about AI, all that stuff, but this is still really necessary. It's not as necessary now that we have deep learning everywhere, but hey, this kind of stuff still happens even with these more sophisticated models. So anyways, just recapping, what's the overall process here? We have supervised learning. It means we have some kind of input variables and some kind of output variable, and we're going to be fitting a model that is the sort of connection between the input and the output, and it's going to learn this statistically, basically by trying to be as least wrong on average as possible. And so that's our sort of setting. We're going to always follow this process of loading the data, doing some sort of like feature engineering, let's call it. I mean, some of this, you could add a little addendum of, instead of just feature engineering, like maybe cleaning the data, but feature engineering, so sort of adjusting the problem, adding an extra sort of variables or making adjustments to variables to basically give our model a better chance at working. After that, we're going to do this train test split, another key step. So that's, we're going to test for overfitting, and then we're going to fit the model finally, and then we're going to evaluate it. And after, we're going to use that in terms of like we're going to quantify the error by using these error metrics, like mean absolute percent error, mean absolute error, and then diagnostic tests, usually like a plot, that can help us find systematic mistakes that our model's making and make adjustments. So sometimes it means we'll pick a different model, or it could mean I do this, more feature engineering. I'll just leave you with a final thought, another feature engineering trick. Like I was saying, like I bet there's a connection between like the sex and like diameter, well, these other ones. I bet there's some, like I was using the metaphor of gasoline in a match, like you have to put them together for it to really work. We could actually introduce whole new sort of columns or features to our data of writing a little code and saying, well, like maybe, the length times this, right? That'd be an interaction if we just multiplied it. So then we have like the female length column. And you would learn a different weight for female length, or for female weight, or male length, male weight, something like this. So you can do these multiplications between the features. That's one way of doing interactions. Or you can just set up code and say like, if maybe split up length for on some critical value. So you can kind of bin it up. Say, okay, if the length is between 0 and 0.1, that's going to be a 1. If it's between zero point 0.1 and 0.2, that's a new feature. Between 0.2 and 0.3. Anyways, you can sort of slice and dice the data, these columns, or introduce new variables that are like interactions between the two by like multiplying them or something like this. And that'll give you these sort of interaction effects, or nonlinear effects. So there's a lot of different, these are all called feature engineering things. These are also little tricks that can improve your data. But anyways, that's the overall view. This is just one long example of trying to predict the age of clams, which we had relative success. But thank you for listening.